Introduction to graphs. Graph is a data structure that has been a subject of intensive study over the past several hundred years. Famous mathematician Euler is credited with doing pioneering work on graph theory. Using a graph representation, he was able to solve the celebrated problem of crossing 7 bridges to the island of Königsberg without using any one of the path more than once. However, many of the important and useful graph algorithms have been discovered over the past 4 decades, almost in parallel with the advent of computers. Unlike other data structures, graphs are often studied as mathematical constructs. As such, much of the terminology and notions associated with graph data structures are borrowed from the discipline of discrete mathematics. In this section, we examine the relevant definitions and concepts. Graph. A graph is a collection of data items called vertices and edges. Vertex stores some kind of data. An edge represents a connection between pairs of vertices. A vertex is sometimes referred to as node or point. An edge is also termed as arc. Suppose A and B represent a pair of vertices in a graph. The edge connecting A to B can be represented as AB, or more commonly as enclosed in a pair of parentheses. In formal theory of graphs, set notation is often used to represent a graph and its associated elements. Thus, a graph G is defined as a set VE, where V is a set of vertices and E is a set of edges. If V1, V2, V3 up to Vn are the vertices, then using set notations we can write. More often, graphs are shown pictorially using diagrams. Typically, a rectangle, oval, or circle represents a vertex. Lines or arcs are used to depict the edges. Suppose, for example, a graph consists of vertices A, B, C, D, and E with edges AB, AC, BC, CD, CE, DE. Figure shows a diagrammatical representation of this graph. It is emphasized that in pictorial representation, the location of vertex is immaterial for some applications. Thus, vertices can be laid out in several ways. For example, this figure is an alternative representation with a different geometrical configuration of the same set of vertices and edges. Although these two pictorial representations give different looks, they represent the same set of data elements in the graph. Graphs are classified on basis of properties of the edges and their orientation. The major categories are undirected, directed, weighted, and multigraph. We now briefly overview the salient features of each type. Undirected graph. In an undirected graph, the edges are not assigned any direction. Thus, there can be at most one edge between a pair of vertices. The undirected graph is used to represent one-to-one relationship among the data elements. Figure shows an example in which all elements are linked together. It can be shown that an undirected graph with n vertices can have at most n into n-1 by 2 edges. The edges of an undirected graph are denoted by unordered pair of vertices enclosed in parentheses. For example, an edge connecting vertices V and U is represented as UV. Note that UV and VU represent the same edge. An undirected graph is also termed as undigraph. A graph in which all the edges are present is called complete graph. By contrast, a graph with comparatively fewer edges is called sparse. Generally, a graph with less than n log n edges, where n is the number of vertices, is categorized as sparse. Directed graph. In a directed graph, each node is assigned a direction. The edges of a directed graph are usually denoted by an ordered pair of vertices enclosed in angle brackets. Thus, the pair UV represents an edge which starts at vertex U and ends at vertex V. The first vertex is referred to initial vertex and the second as terminal vertex. As such, UV and VU represent different edges connecting the same pair of vertices. A directed graph is also termed as digraph or network. Figure shows an example of a directed graph. It consists of vertices A, B, C, D and E and edges AB, BA, AD, ED, CB, DC and ED. Weighted graphs. In weighted graph, the edges are assigned data values referred to as weights. Weighted graphs have several real-life applications. A weighted graph might, for instance, represent cost of transportation between two locations, amount of data traffic between workstation in a network, or distances between two cities. Figure shows an example of a weighted graph. The numbers attached to the edges are the weights. A weighted graph can be directed or undirected depending on the nature of application. For example, a weighted directed graph can represent flight journey between two airports because flight distances between two airports might be different depending on the flight paths for forward and backward journeys. Multigraph. A multigraph is a generalization of a directed graph. In their structure, there can be multiple edges between a pair of vertices. Such edges are termed as parallel edges. Figure shows a multigraph. Observe that there are three edges between the vertices A and B. There are two parallel edges from A to B and one edge from B to A. A multigraph is used to represent a many-to-many relationship among graph elements. Graph paths. A path between a pair of vertices is a sequence of vertices in the graph which are connected by successive edges. We can denote the path by enclosing the list of vertices in a pair of angle brackets. For example, in figure, ABDE represents a path between the vertex A and E. The length of a path is the number of edges that occur along the path. For example, the length of path ABDE is 3. The vertices which have path of length of 1 are called adjacent vertices or neighbor. For example, in this figure, vertices B, C and D are neighbors of vertex A. A vertex is said to be reachable from another vertex if there exists a path between the vertices. In the figure, vertex B is reachable from vertex A or vertex E, but A is not reachable from any other vertex.